Welcome back. Let's practice using spherical coordinates. All right, so here's our first example. We want to convert the point from spherical coordinates to rectangular coordinates. And our point is 8 pi divided by 6 pi divided by 4. Now for all of these examples, I have this sidebar over here for us to reference that has all of the different conversion formulas that we might need to use for converting our coordinates between spherical, rectangular, and cylindrical. Okay, now which formulas we need to use will depend on what coordinates we need to find, but regardless, these are all the formulas we might need to use. Now in this case, we've been given a point in spherical coordinates, and spherical coordinates are always ordered like this. You have rho, the distance from the origin to your point, and then theta, the angle from the positive x-axis, and then phi, or some people say phi, but I say phi, which is the angle from the positive z-axis. All right, so in this case, rho is equal to 8, theta is equal to pi divided by 6, and phi is equal to pi divided by 4. So I'm going to write that down. I find that this helps me determine what formulas I need to use. By writing down explicitly what coordinates I have, I can then see which conversion formulas might be the most helpful for converting those coordinates to rectangular coordinates. All right, so we have rho equals 8, theta equals pi divided by 6, and phi equals pi divided by 4. Now, just to get an idea of where this point is, so that we'll know if our rectangular coordinates are correct once we have them, let's roughly plot where this point would be in the 3D coordinate system. I always like to start with the angle of theta, which in this case is pi divided by 6. That's the angle from the positive x-axis. Pi divided by 6 would just be a small angle, so it might look something like this. We'll call that pi divided by 6. So that would be our angle of theta. And so we know that our point will be in the vertical plane that would cut through that angle of pi divided by 6. So when we consider our angle of phi, which is pi divided by 4, that's the angle from the positive z-axis, you want to measure that from that z-axis in such a way that your point would be in the vertical plane for pi divided by 6. All right, so I'd probably measure that this way. We'd call that phi, which should be an angle of pi divided by 4. And so then if we were going to plot our point, we know that the line segment that would measure the distance from the origin to that point would have a length of 8. That's what rho tells us. So we would have a line segment maybe like this, where that is a distance of 8, and then our point would be on the end there. Okay, it's hard to plot points in spherical coordinates accurately on a 2D surface like we're doing here, but you just want to keep in mind that that distance that we're measuring from the origin to our point, which is represented by rho, would be an angle of pi divided by 4 from the positive z-axis, and that point would need to be contained within the vertical plane that cuts through an angle of pi divided by 6 from the positive x-axis. Okay, so that's where our point is located. Its projection would be in the first quadrant of the xy plane, and the point itself would be in octant 1 of the 3D coordinate system. All right, so if you want to write that down, we are in quadrant 1, octant 1. Okay, so now we have an idea of where our point is, so we'll know when we convert our point to rectangular coordinates if our answer makes sense. All right, so now let's actually work on converting our coordinates. We want to go from rho, theta, and phi to x, y, and z. So what formulas are we going to use here? Well, we want to use the formulas that have isolated x, y, and z, and they're equal to an expression in terms of our spherical coordinate variables. So that would be the first 3 conversion formulas right here. We have x, y, and z in terms of rho, theta, and phi. Okay, so let's start with x. We'll have that x is equal to rho, which is 8, times sine of phi, which is pi divided by 4, times cosine of theta, which is pi divided by 6. Then we'll have y is equal to rho, which is 8, times sine of phi, which is still pi divided by 4, times sine of theta, which is pi divided by 6. And then finally, we'll have z is equal to rho, which is 8 times cosine of phi, which is pi divided by 4. Okay, so now if we simplify, I'll start with x. Sine of pi divided by 4 is a square root of 2 divided by 2, and cosine of pi divided by 6 is a square root of 3 divided by 2. So this is equal to 8 times the square root of 2 divided by 2 times the square root of 3 divided by 2. Now 2 times 2 is 4, so we have 8 divided by 4, which is 2. So this is equal to 2 times the square root of 2 times the square root of 3. You can multiply 2 and 3 underneath the square root to get 2 square roots of 6. So that's the x-coordinate. Now let's work on the y. Sine of pi divided by 4 is the square root of 2 divided by 2, and sine of pi divided by 6 is 1/2. So this is equal to 8 times the square root of 2 divided by 2 times 1/2. And then once again, 2 times 2 is 4, 8 divided by 4 is 2, and so you'll have 2 times the square root of 2. All right, so that is the y-coordinate. And then finally, the z-coordinate, we have 8 times cosine of pi divided by 4. Cosine of pi divided by 4 is the square root of 2 divided by 2. So z is equal to 8 times the square root of 2 divided by 2, and 8 divided by 2 is 4, so this is equal to 4 square roots of 2. Okay, so putting those three coordinates together, we have a final answer of 2 square roots of 6, comma, 2 square roots of 2, comma, 4 square roots of 2. Those are the rectangular coordinates that are equivalent to these spherical coordinates. They both represent the same point in the 3D coordinate system. All right, and that does make sense in this case. We know that our point is in quadrant 1 and octant 1 based on these spherical coordinates. And looking at our rectangular coordinates, all three of them are positive, the x, y, and z. So that means that we are in the first octant of the 3D coordinate system. So that checks out. Okay, let's take a look at another example. Next up, we once again want to convert the point from spherical coordinates to rectangular coordinates. And these are our spherical coordinates, 12, negative pi divided by 4, and then 0. Let's write down explicitly what each of those coordinates are. The first one is rho, the second one is theta, and the third one is phi. So we have rho equals 12, theta equals negative pi divided by 4, and phi equals 0. Okay, now we want to get a rough idea of where this point is in the 3D coordinate system. At least that's something that I like to do. In this case, theta is negative pi divided by 4. We would measure that from the positive x-axis. So that would be halfway to the negative y-axis because that would be negative pi divided by 2. So halfway to that is negative pi divided by 4. So our angle theta takes us here. That is negative pi divided by 4. That is theta. And then our angle of phi is 0. And that's the angle from the positive z-axis, which if it's 0, that means we're not going anywhere, right? That means our point has to be along the positive z-axis. So really, this angle of theta didn't actually matter. We could have had any angle for theta, but if our angle for phi is 0, we're just going to be on the positive z-axis, okay? So we're going to have a point along the z-axis, particularly where the distance from the origin is rho, which is 12, okay? So that's where our point is. So if we do our conversion correctly, we should get rectangular coordinates of 0, 0, 12, right? X and y should both be 0, and the z coordinate should be 12. Let's see if that's what we get. Let's use those same three conversion formulas that we used in the previous example. These first three right here allow us to convert from spherical coordinates to rectangular coordinates. We'll have x equals rho, which is 12, times sine of phi, which is 0, times cosine of theta, which is a negative pi divided by 4. Then we'll have y equals 12, which is rho, times sine of phi, which is 0, times sine of theta, which is a negative pi divided by 4. And then finally, we'll have z equals rho, which is 12, times cosine of phi, which is 0. Okay, now if we simplify, for both x and y, we have sine of 0 within the expression, and sine of 0 is 0, right? So we're multiplying everything in these two expressions by 0, which just produces 0. So x equals 0 and y equals 0. And then for z, cosine of 0 is 1. So we have 12 times 1, which means that z equals 12. So putting those three coordinates together, we get rectangular coordinates of 0, 0, 12, which is exactly what we expected based on our sketch of this coordinate point using spherical coordinates. Okay, so that's our last example of converting from spherical coordinates to rectangular. Now let's do the reverse. Let's convert from rectangular to spherical. For this example, we want to convert the point from rectangular coordinates to spherical coordinates, and our point is 5, 0, 0, so we can very easily plot that in the 3D coordinate system. The x-coordinate is 5, the y-coordinate is 0, and the z-coordinate is 0, so we're just going to be at the value of 5 along the x-axis. That is where our point is located. Okay, so we know that x equals 5, y equals 0, and z equals 0. Now what we want to do is convert these rectangular coordinates of x, y, and z to spherical coordinates of rho, theta, and phi. All right, now we're not going to use these three formulas right here. We use those for converting from spherical to rectangular, but they're not as nice for going the other way around because they are solved for x, y, and z. These equations do not have rho, theta, and phi isolated. There's going to be some nicer equations for us to use for converting from rectangular to spherical. And the first one is this one right here. Rho squared equals x squared plus y squared plus z squared. Let's start with that. We know that rho squared will be equal to x squared, which is 5 squared, plus y squared, which is 0 squared, plus z squared, which is 0 squared. All right, so really, rho squared is equal to 5 squared, and if you take the square root of both sides, you'll find that rho equals 5. And it is just 5, not plus or minus 5, because if you remember from the lesson video, rho is defined to only be positive. It will never be negative. You only consider the positive value for that square root. Okay, so that was easy. Now let's find theta, and the way we'll find theta is by using this equation. Tangent theta equals y divided by x. So let's work on that. We'll have tangent theta equals y divided by x. Y is 0 and x is 5, and 0 divided by 5 is 0. So we have tangent theta equals 0. And tangent is equal to 0 when theta is equal to 0 and pi. Okay, so there's two possible answers here. Theta could be 0, but it could also be pi. Looking at where our point is located in the 3D coordinate system, though, it wouldn't make sense to use an angle of pi because that would take us back here, right? An angle of theta equals 0 keeps us on the positive x-axis, which is where we want to be, right? Theta is measured from the positive x-axis, so if theta is 0, then we don't go anywhere. We stay right there, which is where we want to be. So we can rule out theta equals pi. That's going to happen when you solve for theta in these conversions. You're probably going to find two possible answers, but only one of them is going to be right based on where your point needs to be in a 3D coordinate system for the conversion to be accurate. Okay, so we will go with theta equals 0 in this case. Now finally, we need to find phi, which we will do using this equation. Cosine phi equals z divided by rho. So let's work on that. We'll have cosine of phi equals z, which is 0 divided by rho. Now we know that rho is 5, but that really doesn't matter because 0 divided by 5 is 0. So we have cosine of phi equals 0. And cosine is equal to 0 at pi divided by 2 and 3 pi divided by 2. However, remember from the lesson video on this topic that phi can never be greater than pi. All right, so it's not going to be 3 pi divided by 2. The only answer here is pi divided by 2. Okay, so phi must be equal to pi divided by 2. Yes, cosine would be equal to 0 at 3 pi divided by 2, but phi is not defined for angles bigger than pi. So we just stick with pi divided by 2. All right, so all together, here's our spherical coordinates. We will have 5, 0, and pi divided by 2. Right, we have rho, which is 5, then theta, which is 0, and then phi, which is pi divided by 2. That is our final answer, and it does make sense because if you think about how you would plot this point in the 3D coordinate system, our angle of theta is 0, so we don't go anywhere from the positive x-axis, we stay there. The angle from the positive z-axis is pi divided by 2, that's what phi tells us, and an angle of pi divided by 2 from the z-axis will take you to the xy plane. Right, from the positive z-axis to the negative z-axis would be pi, so half of that, pi divided by 2, takes you to the xy plane. But since we are at theta equals 0, that just takes us along the x-axis. So I'll just label that here. That is our angle of pi divided by 2. And then rho, our distance from the origin, is 5. So everything checks out here. These spherical coordinates are equivalent to these rectangular coordinates. Let's do another conversion. For this example, we once again want to convert the point from rectangular coordinates to spherical coordinates, and our rectangular coordinates are -1, 2, 1. So that means x equals -1, y equals 2, and z equals 1. So let's work on converting these to spherical coordinates. We'll use the same formula as we used last time. Let's start with rho squared equals x squared plus y squared plus z squared. Right, we have rectangular coordinates of x, y, and z, but we want rho, theta, and phi. So let's start with rho. Rho squared is equal to x squared, so negative 1 squared, plus y squared, which will be 2 squared, plus z squared, which will be 1 squared. Now simplifying, rho squared equals 1 plus 4 plus 1. So rho squared equals 6, which means that rho equals the square root of 6. And it will just be the positive square root of 6, not plus or minus. Remember, rho will always be positive. That's how it's defined. And then let's move on to finding theta. We know tangent theta equals y divided by x. So we have tangent theta equals 2 divided by negative 1, right? Y is 2, x is negative 1. 2 divided by negative 1 is negative 2. So we have tangent theta equals negative 2, which means that theta equals inverse tangent of negative 2. Now, negative 2 doesn't correspond to a special angle that we know for our trig functions, so we're probably going to leave our angle of theta just like this. There's no easier way to write this. However, we do want to know roughly how big that angle is. So if you were to put this into your calculator, you would get that it's approximately equal to negative 1.107, and that is less than negative pi divided by 2. Right? That is less than negative pi divided by 2 because pi is approximately 3.14. If you divide that by 2, you get about 1.57. So if we're looking at negative pi divided by 2, that would be negative 1.57, which is clearly bigger than this angle in the negative direction. So what that tells us is that this angle of theta does not go beyond this axis right here, the negative y-axis. All right, when we measure a negative angle from the positive x-axis, we go this way. So if we're not bigger than negative pi divided by 2, then we know that our angle is in this quadrant, okay? So that's where our angle is right now. I'm just going to write theta. That's the angle that we found. And then let's move on to finding phi. Let's use this equation. Cosine of phi equals z divided by rho. So we'll have cosine of phi equals z, which is 1, divided by rho, which is the square root of 6, right? That's what we found over here. Now, here's where things get tricky again. There is no special angle that corresponds to 1 divided by the square root of 6 for cosine. So this is just another ugly angle. We would just represent it like this. You would have phi equals inverse cosine of 1 divided by the square root of 6. And if you plug that in your calculator, you will find that it's approximately equal to about 1.15, which once again is less than pi divided by 2, which is about 1.57. So we know that our angle of phi does not go below the xy plane, okay? Any angle bigger than pi divided by 2 would take you below the xy plane, but since we are less than pi divided by 2, we will be above the xy plane, which makes sense because our z-coordinate is 1, so we would be above the xy plane. All right, so it looks like we have all of our coordinates here, right? We have rho equals the square root of 6, theta equals inverse tangent of negative 2, and phi equals inverse cosine of 1 divided by the square root of 6. However, we need to check to make sure that those coordinates would take us to the same point as these rectangular coordinates. Remember, we have a negative x coordinate, a positive y coordinate, and a positive z coordinate. So in a 3D coordinate system, where does that take us? Well, a negative x coordinate takes us back here along the negative x-axis. A positive y coordinate brings us over here into this quadrant, and then a positive z-coordinate just brings us up above the xy plane. So our point would be somewhere over here above quadrant 2 of the xy plane, and it would also be in octant 2 of the 3D coordinate system. That's not where this angle of theta takes us, right? This angle of theta is taking us to quadrant 4, so we're going to have to adjust that. We're going to have to add pi to this angle of theta, and then that will take us to the right quadrant. Okay, so our point should be somewhere over here, and in order to get over there, we need to add an angle of pi to theta. So our final coordinates here in spherical will be the square root of 6, and then inverse tangent of negative 2 plus pi, and then we'll have our angle of phi, which is cosine inverse of 1 divided by the square root of 6. All right, that is our final answer. Those are the spherical coordinates, albeit pretty ugly, but they are the right coordinates that are equivalent to these rectangular coordinates. All right, this angle of theta takes us into this quadrant, and this angle of phi keeps our point above the xy plane because it is less than pi divided by 2. That's exactly where we want our point to be. Okay, it's in quadrant 2, octant 2. And so that was our last example of converting between rectangular and spherical coordinates. Now we're going to switch gears a little bit and convert from cylindrical to spherical and vice versa. Hey there, real quick, before we take a look at the next example, if you find my tutorial videos here at JK Math to be helpful, then I'd invite you to join my membership site JK Math Plus, where you get access to many perks including bonus content and my exclusive community. The bonus content includes dark mode versions of my videos, extra example problems, and more, while the community is a private space online where you can post questions, have discussions, and study together with me and other members. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I will have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's take a look at the next example. All right, so for this example, we want to convert the point from cylindrical coordinates to spherical coordinates. And our cylindrical coordinates are 2 pi divided by 3, and -2. All right, so remember, cylindrical coordinates are in the form of r, theta, and z. So we have r equals 2, theta equals 2 pi divided by 3, and z equals -2. All right, now converting from cylindrical to spherical is a lot easier than converting from rectangular to spherical, and that's mainly because cylindrical and spherical coordinates share a coordinate, and that is the angle theta. They both have that same coordinate of theta. That does not change. It stays the same between those two sets of coordinates. All right, so we don't need to worry about theta. We just have to convert r and z to rho and phi. Okay, so to convert to rho, we can't use this equation of rho squared equals x squared plus y squared plus z squared because we don't have x and y. But what we can do is use this one down here. We know that r squared is equal to x squared plus y squared. So making that substitution in this formula, you then get this formula, rho squared equals r squared plus z squared. That's what we're going to use here. So rho squared is equal to r squared, so we'll have 2 squared plus z squared, which will be -2 squared. And then simplifying, rho squared will be equal to 4 plus 4, which is 8. So we know that rho will be equal to the square root of 8, which reduces to 2 square roots of 2. All right, and that's just positive 2 square roots of 2. We don't consider the negative root because rho can only be positive. So that's 2 of our coordinates done. We already have theta and rho. Now let's find phi. And we can use the same equation that we used for rectangular because we know what z and rho are, right? Z is one of our given coordinates for cylindrical coordinates. So we don't need another formula for that. We can use the same one we used in rectangular. So we'll have cosine of phi equals z, which is -2 divided by rho, which is 2 square roots of 2. These two 2's will cancel out. So you'll have cosine of phi equals -1 divided by the square root of 2, which is actually just another way of writing the square root of 2 divided by 2, right? If you were to rationalize this by multiplying the numerator and denominator by the square root of 2, you would get this. You would have cosine phi is equal to the negative square root of 2 divided by 2, which is maybe a little bit more recognizable for most of us as a value that corresponds to a special angle. In particular, we know that cosine is equal to the negative square root of 2 divided by 2 when the angle is 3 pi divided by 4. Now, yes, there is another angle if you're going all the way to 2 pi. 7 pi divided by 4 would also be an appropriate angle for when cosine is equal to the negative square root of 2 divided by 2. But remember, for phi, we only consider angles between 0 and pi. So there's only one possible answer here, and that is that phi is equal to 3 pi divided by 4. Okay, and so now we can put our 3 coordinates together, and we'll find that our spherical coordinates are 2 square roots of 2, 2 pi divided by 3, and 3 pi divided by 4. 2 square roots of 2 is rho, 2 pi divided by 3 is theta, and 3 pi divided by 4 is phi. All right, and then just to get an idea of where that would be in our 3D coordinate system, we didn't really need to plot it in this case because we already have our angle of theta. There's nothing for us to really check to make sure we're in the right quadrant or octant. Theta is just theta. It's already given to us. So the one coordinate that might cause us some trouble in terms of locating our point isn't even a factor here. We already know what it is. But if you wanted to quickly plot this point, an angle of 2 pi divided by 3 from the positive x-axis would take you to somewhere over here. That would be theta. And then an angle of 3 pi divided by 4 from the positive z-axis will take you down here. All right, so that is phi, which means that our point will be somewhere down here like this. Okay, it would be below the xy plane because the phi coordinate is greater than pi divided by 2, and it will be below the second quadrant of the xy plane because our angle of theta takes us to that quadrant. Okay, so if you wanted to write that down, you could. We are in quadrant 2, octant 6. All right, remember when you count octants, above the xy plane, it's 1, 2, 3, 4, and then below the xy plane, it's 5, 6, 7, 8. Okay, so our point here, even though it's hard to draw and visualize, it would be in the 6th octant, which is below the second quadrant of the xy plane. Okay, let's look at another example. Once again, we want to convert the point from cylindrical coordinates to spherical coordinates. In this example, our point is 5, pi, 12. So these are cylindrical coordinates, which means that r equals 5, theta equals pi, and z equals 12. Now, once again, because we are converting from cylindrical to spherical, we don't need to do anything with theta. Theta will remain the same. It is pi. What we need to find is rho and phi. And we can find rho using this formula. We'll have rho squared equals r squared, which is 5 squared, plus z squared, which is 12 squared. Now 5 squared is 25, 12 squared is 144. So rho squared is equal to 25 plus 144, which means that rho squared is equal to 169, which is the square of 13. So rho is equal to 13. Okay, now let's work on phi. We want to use this formula once again. We'll have cosine of phi equals z, which is 12, divided by rho, which we now found is 13. And that's not a particularly nice value. It doesn't correspond to any special angles for cosine, or really any trig function for that matter. So in this case, we're just going to solve for phi like this. We'll have inverse cosine of 12 divided by 13, or 12/13. And that's it. If you're curious how big that angle is, you could plug it into your calculator and find that it's approximately equal to 0.39, which is much smaller than pi divided by 2, right? That is less than pi divided by 2. So we know that our point will be above the xy plane. Our point will not be below it. Okay, so altogether, our spherical coordinates are 13, pi, and then inverse cosine of 12/13. And that's it. If you want to take a look at where that point would be in the 3D coordinate system, an angle of pi from the positive x-axis, that's theta, that would take us to the negative x-axis, that is theta. And then this angle for phi is less than pi divided by 2, so we know that our angle will be somewhere above the xy plane. It's kind of a small angle, so it might be something like this. That might be phi. It's just a rough sketch of where it would be, and so then you could draw your line with a length of 13, and at the end of that would be your point represented by these coordinates and these coordinates. Okay, so that was our last example of converting from cylindrical coordinates to spherical coordinates. Now let's do the reverse of that. Let's go from spherical to cylindrical. In this example, we want to convert the point from spherical coordinates to cylindrical coordinates, and our spherical coordinates are 4, pi divided by 18, and then pi divided by 2. So since these are spherical coordinates, we know that the first coordinate is rho, so rho equals 4. Then the second coordinate is theta, theta equals pi divided by 18. And then the last coordinate is phi, so phi equals pi divided by 2. All right, so we've been given rho, theta, and phi, and we want to find r, theta, and z. Okay, we don't need to worry about theta. Theta is going to remain the same between spherical and cylindrical. It's the other two coordinates that we need to convert to different coordinates. All right, but before we do that, let's just get an idea of where this point is. This isn't really all too important for converting between spherical and cylindrical, but I still like to show you where the point would be in the 3D coordinate system. An angle of theta that is pi divided by 18, that's a pretty small angle, so that's not too far off from the positive x-axis. We'll say that it's something like this, that's pi divided by 18. And then if our angle of phi is pi divided by 2, that will take us to the xy plane. So our point will be along this line or this angle in the xy plane, particularly a point that is 4 away from the origin. All right, so you could draw a line segment along that angle that has a length of 4, and at the end of that would be our point. Okay, so now let's convert to cylindrical. I did forget to draw this angle here though. Let me do that real quick. That is phi. But anyway, we want to get a radius r, And so do we have any conversion formulas that are solved for r? Well, we have two of them. We have r squared equals x squared plus y squared. That's not going to be helpful because we don't have x and y. We're working with spherical coordinates, so we want to use this one here. R equals rho times sine phi. All right, so we'll have r equals rho, which is 4, times sine of phi, which is pi divided by 2. And let's solve that right now. Sine of pi divided by 2 is 1, so r is equal to 4 times 1, so r is equal to 4. And then let's find z. We just want to use this formula right here. It's basically the same as this one down here, but just solved for z. So z will be equal to rho times cosine of phi. So we'll have z equals rho, which is 4, times cosine of phi, which is pi divided by 2, and cosine of pi divided by 2 is 0. So z is equal to 4 times 0, which is 0. All right, so putting all those coordinates together, we get cylindrical coordinates of 4 pi divided by 18, because theta stays the same, and then phi is 0. Okay, so those are the equivalent cylindrical coordinates to these spherical coordinates. Let's take a look at another one. Here we once again want to convert the point from spherical coordinates to cylindrical coordinates, and our spherical coordinates are 8, 7 pi divided by 6, and then pi divided by 6. So we've been given rho, theta, and phi. Rho equals 8, theta equals 7 pi divided by 6, and phi equals pi divided by 6. Let's quickly plot where this point would be in the 3D coordinate system. With an angle of theta equals 7 pi divided by 6, from the positive x-axis, that's going to take us a little bit past the negative x-axis, which is an angle of pi, right? 7 pi divided by 6 is bigger than that. So we will be back here somewhere in that third quadrant of the xy plane. That is theta. And then for phi, we are at an angle of pi divided by 6 from the positive z-axis. So that is an angle like this. We'll call that phi. And so the line segment that would have a measurement of 8 from the origin to our point would be in the vertical plane at this angle of theta, and it would be an angle of pi divided by 6 from the z-axis. So it would look something like this. It's not perfect, but that would take us to our point, given that that is a measurement of 8. Okay, but now to convert to cylindrical coordinates, we'll use the same formulas we used in the previous example. We want to use r equals rho times sine phi and z equals rho times cosine phi. So we'll have r equals 8 times sine of pi divided by 6, and z equals 8 times cosine of pi divided by 6. Okay, we only need to convert to r and z because theta is the same between spherical and cylindrical. Now, sine of pi divided by 6 is 1/2, so r is equal to 8 times 1/2, which means that r equals 4. And then cosine of pi divided by 6 is the square root of 3 divided by 2. So z equals 8 times the square root of 3 divided by 2. 8 divided by 2 is 4, so z is equal to 4 square roots of 3. All right, and then putting all of our coordinates together, we have r equals 4, then theta equals 7 pi divided by 6. That's the same angle that we were given. For the spherical coordinates, it remains the same. And then we have a z-coordinate of 4 square roots of 3. All right, those are the cylindrical coordinates that are equivalent to the spherical coordinates. They will represent the same exact point in the 3D coordinate system. Okay, so this was the last example of converting points in spherical to the other coordinate types and vice versa. Now we're going to look at equations. First up, we want to convert the equations in rectangular coordinates to spherical coordinates and identify the surface. And we have x equals 3, y equals 2, and z equals 4. Now, all three of these, hopefully you recognize them to be planes, right? When you just have x equal to some constant, y equal to some constant, or z equal to some constant, that represents a plane in the 3D coordinate system. So the surfaces that we're working with here are pretty simple. We've already identified them. We know they're all planes. So I'll write that down here. All planes. But now we actually want to convert them to spherical coordinates. And so to do that, what we need to do is get these equations from being in terms of x, y, and z to being in terms of rho, theta, and phi. And to do that, we just want to use these first three equations here that tell us what x, y, and z are equal to in terms of spherical coordinates. So let's replace x, y, and z with what they're equal to from these formulas. For x, we'll have rho times sine phi times cosine theta equals 3. For y, we'll have rho times sine phi times sine theta equals 2. and for z we'll have rho times cosine phi equals 4. Now technically, you could stop there. These would all be correct answers. They are all equations in spherical coordinates because the only variables involved in these equations are rho, theta, and phi, right? You don't have to have all of those variables. In this one for z, you just have rho and phi. That's okay. You don't have to have all three variables. But the point is, there are only spherical variables in this equation. Okay, so we're good. However, it is good practice to try to solve for rho when possible. That's sort of the way we like to solve for spherical equations. If you can get rho equal to some expression, that would be ideal. So to solve for rho in each case, we have to divide both sides of each equation by these trig functions. So for x, we'll have rho equals 3 times 1 divided by sine of phi times 1 divided by cosine theta. For the y equation, we'll have rho is equal to 2 times 1 divided by sine of phi times 1 divided by sine of theta. And then for the z equation, we'll have rho equals 4 times 1 divided by cosine of phi. Now, once again, you could leave these equations in this form. However, you can simplify them using some trig identities. Remember that 1 divided by sine is cosecant and 1 divided by cosine is secant. So our final answers here will be that rho equals 3 times cosecant phi times secant theta, and then rho equals 2 times cosecant phi times cosecant theta, and then rho equals 4 times secant phi. Okay? Not the nicest equations, that's for sure, but those would be the equivalent equations in spherical coordinates for the equations that we were given in rectangular. And hopefully it makes sense that these are more complicated because when you're in the rectangular coordinate system, a surface that is rectangular, such as planes, will be easier to represent, whereas in the spherical coordinate system, a surface like a sphere is going to be a lot easier to represent, okay? And I think you'll see that with our next example. All right, so next up, we want to convert the equations in rectangular coordinates to spherical coordinates and identify the surface. And our two equations are x² plus y² plus z² equals 49, and x² plus y² equals 25. Okay, so let's start with the first one here. Hopefully you can identify this immediately as representing a sphere, right? If you have x² plus y² plus z² equals some constant, that represents a sphere where the square root of the constant is the radius of the sphere. And so this is very clearly representing a sphere, which means that the spherical equation will be very nice. All right, and you can see how that's going to develop because we know that rho squared is equal to x² plus y² plus z². So we can replace x² plus y² plus z² in this equation with rho squared. So rho squared is equal to 49, and you can take the square root of both sides and find that rho is equal to 7. All right, that is the spherical equation equivalent to this rectangular equation. Both of them represent spheres that have a radius of 7. Now for this equation, things are a little bit trickier because we just have x² plus y². There is no z variable here. And so if you remember back to a couple lessons ago when we talked about cylinders in 3D space, that is exactly what we have right here. Whenever you have a rectangular equation that represents a surface and you only see two of the three variables, you have a cylinder. In this case, the trace of that cylinder would be a circle because this would be the equation of a circle in the xy plane, right? x² plus y² equals the radius squared. In this case, that would be 5. So this is a cylinder that has a trace of a circle in the xy plane with a radius of 5 that would be projected along the z-axis because the z variable is missing from this equation. Okay, so I'll write that down at the end, but to convert this to spherical coordinates, we're not going to be able to use rho squared again. So it looks like it's going to be a bit tricky to convert it to spherical. Something that you might be tempted to do is plug in what x and y would be equal to in terms of rho, phi, and theta, and then square that and see where that takes you. But you can actually do something a little bit nicer, something that will be faster to getting a nice spherical equation. And that is to first convert this to be in terms of cylindrical coordinates. This is actually something that I highly recommend for a lot of these types of problems. If you're converting a rectangular equation to a spherical equation, it might be helpful to first convert it to cylindrical and then convert it to spherical. All right, so we know that x² plus y² is r². So this would be r² equals 25. And then we can replace r with what it's equal to in terms of rho and phi. All right, r equals rho times sine of phi. So we'll have rho squared times sine squared of phi equal to 25. And then if we take the square root of both sides of the equation, we'll just have rho times sine of phi equals 5. And then we can solve for rho by dividing both sides by sine of phi, which will produce cosecant on the other side, right? So you'll have rho equals 5 times cosecant of phi. All right, so that would be the equation in spherical coordinates. And as I mentioned earlier, it does represent a cylinder with a trace of a circle that has a radius of 5 in the xy plane that is projected along the z-axis. Okay, let's take a look at another example. So for our next example, we want to convert the equations in spherical coordinates to equations in cylindrical and rectangular coordinates, and then identify the surface. All right, so we have 3 spherical equations here, one for each of the different variables. So we have rho equals 5, theta equals 3 pi divided by 4, and phi equals pi divided by 2. Let's start with rho equals 5. This should hopefully be the easiest one. You know that whenever you see rho equal to a constant, that represents a sphere because rho is the radius of a sphere. So we know that that's what this represents. But to get it in terms of cylindrical and rectangular coordinates, what we want to do here is first square both sides of the equation. That way we get rho squared equals 25. And then we can change rho squared to be r squared plus z squared for cylindrical, and then x squared plus y squared plus z squared for rectangular. All right, so for cylindrical, you'll have r squared plus z squared equals 25. And then for rectangular, you'll have x squared plus y squared plus z squared equals 25. All right, so that's it for that equation. Now let's move on to this equation. Theta equals 3 pi divided by 4. That's just going to be a vertical plane that cuts through that angle of 3 pi divided by 4. Whenever you see theta equal to an angle, that is a vertical plane. That's just something you have to learn. But to convert it to cylindrical and rectangular, what we want to do is introduce tangent, because we know tangent theta equals y divided by x. So if we take tangent of both sides of the equation, we'll have tangent theta equals tangent of 3 pi divided by 4. And tangent of 3 pi divided by 4 is -1. So we'll have tangent theta equals -1. And then we know that tangent theta is y divided by x. So we'll have y divided by x equals -1. And then you could solve for y by multiplying both sides by x. And you'll have y equals -x. All right, so that's the rectangular equation. And you might be wondering, well, what's the cylindrical equation? And to that, I would say you're thinking too hard because it's right there. It's theta equals 3 pi divided by 4, okay? Remember that for cylindrical and spherical, theta doesn't change, it's the same. So an equation in spherical that just involves theta is also an equation in cylindrical. Okay, so we don't need to do anything with that for cylindrical. It is just theta equals 3 pi divided by 4. And then finally, let's take a look at this equation. We have phi equals pi divided by 2. This one can be a little bit trickier, but what we probably want to do here is introduce cosine, because I know that cosine of phi is equal to z divided by rho, and then we can just replace rho with an expression in terms of cylindrical or rectangular coordinates. So I'm going to start with that. I'll take cosine of both sides of the equation. So we'll have cosine of phi equals cosine of pi divided by 2. But now cosine of pi divided by 2 is 0. So we have cosine of phi equals 0. But then we want to replace cosine phi with z divided by rho. All right, so I'm just going to do that right here. I'll erase cosine phi and write in z divided by rho. But it doesn't matter what rho is. If we multiply both sides of the equation by rho, you'll be multiplying 0 by rho, which just gives us z equals 0. And that's actually it. That's the final equation here, equivalent to this equation in spherical coordinates for both cylindrical and rectangular, right? Both cylindrical and rectangular work with a z variable, so if we have z equals 0, that is an equation in both rectangular and cylindrical coordinates. So that's our answer here. That is both rectangular and cylindrical. That is good to go. All right, and what it represents is a horizontal plane. Right? It's a plane that cuts through the value of z equals 0, which really, that's the xy plane, if you want to get really specific. Okay, let's take a look at one more example for this video. All right, so for our last example, we once again want to convert the equations in spherical coordinates to equations in cylindrical and rectangular coordinates, and then identify the surface. And we have rho equals 4 times cosine of phi, and rho squared times sine squared of phi minus 2 times rho squared times cosine squared phi equals 1. All right, now let's start with this one over here. At first, it seems a little bit confusing on how we would convert this to both rectangular and cylindrical, but something that I notice is that we do have cosine of phi, so maybe if we multiply both sides by rho, then we'll have rho times cosine of phi, and that is equal to z. So let's do that. If we multiply both sides by rho, we'll have rho squared equals 4 times rho times cosine of phi. And then to get in cylindrical, we can replace rho squared with r squared plus z squared and replace rho times cosine of phi with z. So we'll have r squared plus z squared equals 4 times z. And I would just keep it like that. That would be our answer for cylindrical coordinates. That equation is in terms of r and z, so we're good to go. But then for rectangular, things get a little bit trickier. We can replace r squared with x squared plus y squared. So we'll have x squared plus y squared plus z squared equals 4z. And technically that would be the equation in terms of rectangular coordinates, but it's not entirely clear what surface that represents, at least in terms of specifics. I can tell that it's a sphere because we have x squared plus y squared plus z squared, but what it's equal to is another term involving z. So what that means is we need to bring this term over to the other side of the equation and complete the square for z, and then we'll have the equation of a sphere that is not centered at the origin. All right, that's what's going to happen here. So if we do that, we'll have x squared plus y squared plus z squared minus 4z equals some constant value that's going to depend on what we need to add to complete the square. To figure that out, you take the coefficient of the degree 1 term, which is -4 here, you divide it by 2 and square it. Dividing it by 2 gives you -2, squaring it gives you 4, so we want to add 4 to both sides of the equation. All right, so now we've completed the square. We can now factor these z terms. It will give us z minus 2 squared. If you're curious where I got the -2 from, it's whatever you get when you divide this value by 2. -4 divided by 2 was -2, so that's going to be our factor. Anyway, this is what we'll get. We'll have x squared plus y squared plus z minus 2 squared equals 4. And so that right there is our rectangular equation, and it represents a sphere with a radius of 2, which would be the square root of 4, and it's not centered at the origin, it's centered at 0, 0, 2, all right? Whatever value is being subtracted from each of your variables, that is the corresponding coordinate of the center. Okay, and then finally, let's look at this equation here. It looks pretty complicated, but it's actually pretty easy. All you have to recognize is that rho times sine of phi is equal to r. So this right here is just r squared. So that becomes r squared, and then you're subtracting 2 times rho squared times cosine of phi squared, which is just z squared, right? Z is equal to rho times cosine of phi. So phi squared times cosine squared phi is z squared. So you have 2 times z squared, and then that's equal to 1. That's your equation in cylindrical coordinates because you're now entirely in terms of r and z. Technically, you could have theta as well, but theta is not there in this case. So that's good. And then for rectangular, you just have to change r squared to be x squared plus y squared. Okay, so you'll have x squared plus y squared minus 2z squared equals 1. And that is the equation in rectangular. But what does it represent? Well, if you remember your quadric surfaces, this equation right here is clearly in the form of a hyperboloid of one sheet, right? The general form of a hyperboloid of one sheet is that you have 3 squared variable terms, 2 of them are positive, and 1 of them is negative, and they are equal to a constant. And with that, this was the last example for this video, but I do have a couple more examples available on my membership site. You can learn more about that by heading on over to my website at jkmathematics.com/plus. So if that's something that interests you, feel free to look into becoming a member. If you have any questions, feel free to leave those in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.